website. You can have a look at the benefits there. All of the webinars in this series are free for IGBC members to download from the website. And there's a CPD certificate associated with this webinar. You should find that now on the handout section on the right hand of your screen. So you can download that now. So I'm delighted to welcome our speakers here today. We have with us Edith Blennerhassett and Louis Gay Tarzona from Arab. Please feel free to type your questions in the chat box, and we'll be answering a selection of the questions at the end. So thanks for attending, and I'm going to hand over now to Edith.
Thank you, everyone, and good afternoon. Welcome to this IGBC webinar. My colleague, Louis Gay Tarzona, and I are going to discuss the challenges of meeting the renewable energy ratio requirements set out in the New Building Regulations Part L 2017. So we'll very briefly touch on the background to delivering near zero energy buildings. We know the first webinar looked at Part L in a lot of detail. We'll just talk maybe about some of the renewable energy technologies being considered, and then we'll run through a number of case studies for a variety of different building types. So the background is obviously we have a new Part L 2017 published almost this time last year, and within that there is a significant improvement in our buildings from an energy perspective, from a carbon emissions perspective, and the main change which we're focusing on today is the introduction of a need to meet some either 10 or 20% of the primary energy demand of the building through renewables, and the 10% relates to if you can improve by 10% on the energy requirements, then you can reduce the renewable energy requirements. So the general approach we would say to producing a low energy building or a sustainable building is set out on this slide. Be lean is about firstly making the building do as much as it can to moderate the environment of the building. So that could include high levels of insulation, limiting thermal bridging, providing a high degree of air tightness, and passive solar design, which would include having excellent daylight and solar shading to avoid overheating. The next step then, once you've done that with the building, make the building as good as it can be, is to choose very efficient building services systems, mechanical and electrical systems, lights, air handling units, fans, pumps, and so on, to deliver the environmental and energy requirements of the building. And then the final part is to meet some of the energy demand through renewables. And so if you drive the energy requirements down, obviously the requirement for renewables gets smaller. I just thought I might run through some of the main technologies that are being used to deliver the renewable energy ratio on non-domestic buildings. This doesn't cover everything, but as I say, it covers what you might call the norms. Photovoltaic panels, solar thermal panels, wind power, combined heat and power plant, biofuel and biomass, heat pumps, and hydro water source heat pumps. So I just thought I'd run very briefly through those technologies. PV panels obviously make electricity from sunshine. In terms of their efficiency as a technology, they're probably, the commercially available ones are somewhere maybe between 10 and 15% efficient, which means that's how much of the sun's energy they convert into electricity. So arguably they're not a very efficient technology. I think when you couple that to the fact that Ireland doesn't have a very great solar resource, and then on a lot of sites there might be issues with where you can site a PV panel in terms of maybe overshadowing from adjacent buildings, or the orientation might not be the most ideal orientation. It's hard to get good efficiency from them, and so I would say they're still quite a costly technology, although costs have come down significantly. But in terms of looking at things from a payback perspective, it's quite difficult to show what you might call commercial paybacks for PV panels. And the slides there just show an array of 30 square meters on the mansion house and some on top of a church building over in the UK. And at the back of the mansion house slide, which is the one on the left, you can see there's an array of solar thermal panels, which was a 10 square meter array. So that was the next technology I was just going to mention, which is solar thermal panels, which make hot water from the sun's energy, and that can be used either for general hot water use or indeed put into heating in the building, which would be more unusual. Solar thermal panels are about 30% efficient in terms of the conversion of the sun's energy, and they're generally useful where you have a high hot water demand, and including through the summer months. So they generally would be seen more on residential buildings and perhaps hotel buildings or swimming pool buildings where there are lots of showers. Wind turbines, highly unusual renewable technology to deploy, in particular in city areas. I've shown there a building in Elephant and Castle in the UK where were 3 9-metre diameter turbines put into the top of the building as with the aim of delivering 8% of the building's energy requirements through wind energy. I understand those turbines have had a kind of a checkered history in terms of their operational reliability, and the slides on the right are the Lutyens buildings out on Lambay Island, where there's a 25 kilowatt wind turbine delivering electricity into those buildings. They're off grid, so, and obviously there's plenty of space out on Lambay, so wind turbines work best obviously where they kind of have they're in the clear and the open air, because the power generated is proportional to the velocity cube, so they need a good, they need to be out in the open air with a good wind flow. Combined heat and power is not actually a renewable technology in that it's not free energy, but it is a very efficient technology, so it is considered a renewable under the building regulations. And a combined heat and power plant generally would be, in Ireland anyway, powered by natural gas, which would drive a turbine to produce electricity, and then the waste heat from the electricity production is captured and used in a building for heating or hot water. So it's the reclaim of the heat that makes it considered a renewable technology. It's probably only efficient if you are using the heat, and so again, similar to solar thermal panels, the areas where you might deploy combined heat and power tend to be places with high hot water demand that's constant through the year, such as hospitals or hotels or swimming pools. And in those kinds of buildings, they would pay. A CHP plant would pay for itself quite quickly. But Lewis will talk a bit more about decarbonising the grid, and in terms of carbon emissions of some of these technologies, where they'll sit as we decarbonise the grid more. Biomass boilers or biomass heat or energy from biomass, you can use biomass to fuel a CHP, but generally we're seeing biomass being used just as a fuel for heating. You tend to need a lot of space for the pellet or the wood chip stores. There's ash produced through the burning of the pellets, and that needs to be removed, so there's more maintenance. Boilers are not as efficient as, say, high efficiency condensing boilers. The fuel is relatively inexpensive, but again, in city centre sites, due to the need to get, say, trucks in for deliveries and the space take for the storage of the fuel, they tend not to be the favoured technology from a renewable perspective. They are considered carbon neutral simply because the carbon that is fixed in the biomass products as they grow, whether it be willow or crops or so on, is then released when you burn it to create the heat, and that's considered a carbon neutral solution. Heat pumps are becoming, I would say, one of the main favoured technologies to deliver renewables into buildings. A heat pump is, again, not a renewable as such. It's just a very efficient technology if used in the right way. But say a standard heat pump, a geothermal heat pump that would take energy from the ground and upgrade it to deliver, say, heating or cooling into a building, would have if you put 1 kilowatt of electricity in theory, you can get 4 kilowatts of heat out. So it's very efficient from that perspective. There's different types of heat pumps. There's the one shown on this slide is, geothermal heat pump, which will take heat from the ground through a closed loop borehole sunk into the ground, and the boreholes tend to be about 150 meters deep, and so you can have quite a significant number of boreholes to deliver energy to a large scale building, because you get on average about 10 kilowatts, depends on the ground conditions, but out of a 150 meter deep borehole. So that's quite a lot of drilling for quite a small amount of heat energy. Instead of drilling into the ground, if you have, I don't know, something like a car park and you have a big surface area, you can put the collector pipes horizontally into the ground and pick up the heat from the ground in that way. Or if you have a water, if you have a lake or a river or water flowing through the ground, you can pick up the heat from groundwater and upgrade it for use in the building. Air source heat pumps, again, are becoming a very popular technology, and these take heat from the air and upgrade it to deliver energy, heating or cooling into the building. The coefficient performance tends to be a bit lower than the ground source heat pumps, but they're more economical, I would say, because you're not drilling boreholes into the ground or needing a huge, big surface collector area. But from a heating perspective, in the kind of depths of winter, they're not at their most efficient. They're probably at their most efficient above, say, 7 degrees centigrade. So, at the time when peak heating is happening, they're not delivering their peak efficiency. I mean, there are other ways, I suppose, that you can source air for an air source heat pump. If you have a building that has a very high internal heat gain room, like a computer room or an IT room or a laundry, you could put an air source heat pump in that room and take the heat from that room and upgrade it and use it to heat the building. So that can work very well and be extremely efficient. And another domestic hot water is often produced as well now by air source heat pumps, and generally the domestic hot water production is separated from heating production, and that's because domestic hot water tends to be at about 60 degrees centigrade for Legionella control, and so the heat pump to deliver that high temperature heat is not going to work as efficiently as it might for delivering space heating, where you can deliver it at, say, 30 or 40 degrees centigrade. So it's good to separate those two cycles so that you're getting the best efficiency from the heat pump when you only need it for heating. So just very briefly, before I hand over to Lewis, I'll just mention a few case studies. This was when the Part L came out first. We took one of the buildings we've worked on. This is a 16,000 square metre office building in Dublin city centre, which had 4-pipe fan coils, gas-fired boilers, water-cooled chillers, very standard, speculative office standards, low specific fan power on air handling units, heat recovery, and LED lighting throughout. And we took the different technologies and tried to apply them to the building to see what renewable energy ratio they would give us. So if we covered the roof with PV, which is obviously not very practical because there's probably plant and other things up there, we would just scratch in at the 10% renewable energy ratio. Solar thermal, because it's being sized just to meet the hot water requirements, because otherwise it's wasted energy, could only meet 7%. Wind, again, it wasn't the right regime for a wind turbine, so we tried to make a stab at what the wind turbine might be, but couldn't really deliver much renewables through wind on the site. And again, combined heat and power just sized towards hot water load wasn't giving us very good results. And so in the end, biofuel and biomass, again, city centre site and storage would be restrictions on using those technologies in the building. So heat pumps is probably the favoured option in terms of looking at what the solution to that building would now be under the new regulations. And then the second case study is a building in London called the Crystal. This is a building, it's an exhibition centre based on exhibitions on renewable resilient cities. It's a Siemens developed building, and they set a very high brief to have everything sustainable within the building and a demonstration for their own technologies. Now in the UK there isn't a requirement to meet 10% or 20% renewables for buildings, but people are doing that in various ways to maybe meet BREEAM or LEED targets, or indeed just to make a very strong statement about sustainability. So the starting point again was to work with the fabric and make it as efficient as possible. So whilst the building looks quite glassy, it is in fact only 30% or 36% transparent, very high degree of air tightness, and very high levels of generally of insulation throughout. But the kind of technologies deployed are generally a lot of the ones we've already spoken about. Very deep boreholes into the ground for the building. The piles for the building were also used to take energy from the ground. There's solar thermal panels delivering hot water. There's a very large array of PV panels. And there's battery storage, which again Lewis will refer to as he goes along. So the renewables generate intermittently, and certainly in Ireland at the moment we can export that electricity back out to the grid if we're not using it, but we don't get paid for it. And so in a way, if you're generating energy, it's nice to store it, and so that you can use it. You've paid for the technology, so you use it for your own benefit. So I think battery storage is something we're going to be seeing more of as we implement more renewables in our buildings. Those are just some images of just the interior of the Crystal. And then this next building is called the White Collar Factory, which again is a speculative office development in London, designed again with each facade treated differently from a solar shading and a daylighting perspective. The building has a mixed mode approach, so it's naturally ventilated through spring and autumn, and then mechanically ventilated in winter, and in summer months heat recovery in winter, and obviously in summer better impact. And then there are embedded coils in the slab to deliver cooling into the spaces. That just shows the 6 metre zone, perimeter zone, that can be naturally ventilated in the shoulder seasons. One of the important features of this building is that it has exposed soffits, so it has exposed concrete, which helps to moderate the temperature. And again, in Ireland, in our developer market, that would be an unusual feature. Owner-occupiers might do it, but a lot of developers still want false ceilings, and so that means that you don't have access to that thermal buffer in your design. That was a prototype the client built to test the solutions, and this shows the internal temperature, staying fairly steady as the external temperature comes and goes. So that building achieved 32% reduction on the UK Part L, but maybe only 5% from renewables, which was a PV solar thermal system, and then had LEED and BREEAM outstanding. So at this point, I'll just hand over to my colleague Lewis to move through some more detailed case studies.
Hello, everyone. So I'm Luis Sona, and we're going finishing the presentation after the first 2 case studies presented by Edith. I will finish up with presenting 2 additional case studies. These are 2 projects that ARUP has carried out, was presently carried out right now, complying with the NZEB regulation, and they bring in different design items that we are happy to present to you for you to apply in elsewhere. So the first one is going to be a college education application, and the second one, the case 4, is going to be a healthcare application, so we can bring different uses of buildings to the table. The first one, as I say, is an office, education building. It's located in Dublin. It needs to comply, is BREEAM excellent, and it needs to comply with NZEB. The number of items, there's no need to get into detail, just a bit of a high-level introduction of the concepts we are going to talk about. So we're going to talk about BREEAM, decarbonization of the building in terms of the electric network is going to be decarbonized. What's the implication of that? Hybrid ventilation, life cycle cost to evaluate systems, the different renewable systems, battery storage, phase change materials. So those are that's high level. But there's no need to get into detail in this slide. It's just to let you know that we aim to introduce you these items to you in this case study. So this building aimed to comply, as I say, with BREEAM, also with the NZEB. And what's the implication of that? The implication of that is that first, NZEB requires between 20 and 10% renewables energy to cover the energy of the building, point 1. Point 2, the BREEAM requires to be around, in order to get to the BREEAM excellent rating, the design of the building, the energy of the building needs to be even better than the NZEB. So that gets things even more difficult from the design point of view. So right now, if anybody wants to design a BREEAM excellent building, it needs to be much better than NZEB. So that's a challenging design brief, and that was the case for this building. As well, it needs to be, this a public building, we cannot forget that it needs to be BR83 rated building. Also, it's also to bring into the table that the design needs to be aligned with the Irish National Plan. And what do I mean by that? Well, the National Mitigation Plan is a high-level energy document set by the Irish government. But if you have the opportunity to read it, it also refers to the building sector to be decarbonized in the future. And one of the items it mentions is the uses of heat pump. That as a means of energy efficiency. So that's one of the things as well. That so in liaison with the national mitigation plan, heat pumps will be also considered in order to mitigate the energy emissions at national level in Ireland. Okay, the decarbonization of the network. What do I mean? What do we mean by that? Okay, so if that means that we expect or we hope that the electric emissions of the carbon emissions of the electricity produced in Ireland should decrease in time. This is due to the implementation of more renewable production sources like wind turbines in Ireland. And we are comparing the carbon emissions in the UK and the ones in the left, and which are expected to fall from around 300 to 200 as a number. And in the right, you have the presented available data from Ireland. It's not that clear that yet it has not been published what is the expected fall of emissions in Ireland yet, but we expect that they will fall because of the increased number of renewables installed. The number of carbon plants should be decommissioned as we expect so, and I'm just saying that we understand that would happen, and more and more renewable energy will be produced in gas as well, but also less carbon production, but more renewable. That means that the electricity emissions in Ireland, we expect them to fall. What does it mean? Well, that if we compare, for example, the emissions consumed in time from a boiler against a heat pump, if the boiler consumes gas and the emissions of gas keep constant in time, then the emissions are, as you see in the yellow line. But if the emissions of electricity fall in time, the decarbonization of Ireland gets into place, and then there's more and more and more renewable energy produced by the wind turbines, as an example, then the heat pump which consumes electricity, the emissions will fall every time the electricity emissions fall. So if you install a heat pump in your building, and the electricity emissions fall, then the emissions of the building will fall as well. That's assuming that the emissions of electricity in Ireland are going to fall. The rate of falling, we don't know. It's up to be published. But we understand that is in line with the national mitigation plan that we just mentioned before. We understand that the decarbonization of Ireland needs to happen. Also, there are a couple of things as well to have in mind in terms of designing a low energy building. One is the design temperature, the room design temperature, and you see there in the left is an excerpt from IGBC TM52, which is the design criteria for naturally ventilated buildings. And in summary, there's no need to get into detail. Means that in summer, if the outside temperature is around 20, the average, then your internal design temperature could be up to 28 to have constant, to keep comfort conditions. There's 3 criteria. There's no need to get into detail at this stage, but this high-level point that why cannot we build more naturally ventilated buildings with assuming that the room temperature will raise over the classic 24. Let's start to think about that. That was the case of this building. So it's a matter of convincing, explaining the situation to the client, and proposing the system, etc., etc., etc. IGBC TM52 is also mentioned in the new Partel and the NZEB text. If you find it, if you read it, you will find it there. And also another item to be considered is the feature that's the image on the right of the slide. Is that for this particular building, we are designing for overheating in this particular case for future weather data. What does it mean, future weather data? Where we are assuming we are not using the Dublin present weather data, which available weather data is Dublin 89. We are using the Manchester weather data of 2050, one of the many that are available by IGBC. That means that we are expecting that the outside temperatures in summer in Ireland will be similar to the ones in Manchester as the proxy weather data, and those weather conditions in summer showed that outside temperature will be around, more frequently will be around 20, up to even 32 degrees. And that's the expected weather data published by IGBC for Manchester. Will that happen in Dublin? Well, I mean, Manchester is nearby Dublin, so maybe it's not 32, maybe it's 30, maybe they are not 10 days, maybe, but weather warming is happening. So we are, in this particular building, we are designing for future weather data, which I suggest that has been taken into account. Getting into other items that we already mentioned, efficient shape of the building needs to be studied at the beginning. Why efficient shape of the building needs to be studied at the beginning? Because if you have a low energy building, then the requirement for your renewable gets lower. So at this time, 4 years ago, there was not really a need to optimize the shape of the building, because now we have the renewable requirement. Then the base energy of the building needs to be as low as possible, so the renewable target is as low as possible. So the shape of the building needs to be studied. That goes along as well with also the classic passive design measures like increased insulation and solar shading, glass treatment, etc., etc. Available renewable energies, they're already been mentioned. In this particular case, we went for heat pumps and PV panels. That means that we disregarded CHP, the boiler. This building doesn't have any boiler. We go with air handling units that ventilate the particular labs of this building. We go with very efficient LED lighting. That's very important as well. It has a lot of impact on the NZEB results. And lighting control, don't never forget about the lighting levels, and trying to specify maybe as low as possible. From the energy point of view, comfort will be another matter, but from the energy point of view, looking for the lower levels possible. Heat pumps, this building is all heat pumps, as I say, no gas, and PV panels. PV panels were helping, but they were not the main players. The main players in order to comply were the heat pumps and the lighting, efficient lighting, and efficient ventilation, which I will get in a minute into that. As I say, no CHP. And that was set by the NZEB, which is carbon emissions requirement. So the previous slide was setting that the design was driven by a low carbon emissions. That's good, that's fine. But then we have the client saying, okay, I have to comply with NZEB. That's fair enough. But do I have to pay? How much do I have to pay for that? What is my operation cost in the future? Which is my payback? Does it really make sense in terms of operation in 20 years to spend all that money at the beginning to have such efficient systems, and it will pay back? I mean, it will be, what's my long-term, which is my accumulated cost within 20, 30 years? And that's what this particular client was saying. Okay, so in order to show that side of the decision making when you're selecting an energy system, then we carried out a life cycling cost assessment. Basically, that life cycling cost assessment compares the accumulated cost of different heating systems. In this particular case, as you can see in the slide, is an air source heat pump. An underground, which as mentioned before, is a heating system that gets heat from the water running below the site. And also it was compared to a gas boiler system. And basically, what you show to the client is these kind of things. Don't pay much attention to the numbers. There's no need to. But the concept is that you have solutions that they are at the year one. The capital cost could be higher than the blue solution. There's not even need to it's just solution A against solution B. So you have solutions at the capital cost, which could be the heat pump, could be very expensive at the beginning, but then in time, because you have lower consumption, lower electric cost during the years, then your accumulated cost, which can be transferred, could be calculated as the NPV or net present value, your accumulated cost during 15 years, 20 years could be lower than the alternative solution, which could have lower capital cost. And that's the exercise that puts in the table the financial side of it, not carbon analysis, but financial cost analysis in time, accumulated cost. Okay, getting into again. I move myself out of the financial analysis. I move back into the solutions that was mentioned in any efficient solutions to be considered in a low energy building. This is cross ventilation, cross natural ventilation, but in this particular case, it's hybrid ventilation. Hybrid ventilation, basically, in this particular building, takes air from the facade through a louver, gets it into the air, into the space. These are classrooms, and then in this particular building, it was transferred into the atrium. So the hot air from the classrooms, it could be transferred into the atrium and exhausted to the top of the atrium. And so the atrium didn't need to be heated, additionally be heated. The classrooms are naturally ventilated, but when I say hybrid ventilation, means that there's it's a kind of a box that you see there inside the classroom that is able to naturally ventilate, but when it gets too hot or too busy, the occupancy rate gets too high, CO2 sensors detect that and then supply more fresh air to lower the CO2 concentration. You can set the target to 800 or to 1000 ppm. It was mentioned in previous meetings, and then if you reach that target, then you supply more air. So the fresh air supply modulates depending on the occupancy rate. Another low energy system that should be considered, and is relatively new, is the use of air handling units with a heat pump. This will be an efficient system, but it also uses a heat pump. In that sense, it's heat pump energy, and being heat pump energy is renewable energy, and that ticks the box of the RER compliance. So we're trying to do two things at the same time, is like complying with the renewables target and then being efficient. So this system should be, I think, is one of the items that could be considered in your designs. Another low temporary energy system is already mentioned, is heating or cooling the slab through embedded pipes running through. It's a low response system, but it's efficient in the sense that it connects, it uses water not very cool or not very hot. And that's exactly what the heat pump want. They want water relatively not very hot, sorry. They like to supply water at 40, 45, 50 degrees. If you supply with a heat pump at water over 60, 70, then the heat pump doesn't like it in terms of efficiency. So you can supply water to the slabs at maybe around 30 degrees, 20 degrees, and you still can heat the building. Obviously, this system requires exposed slabs, exposed surfaces, so the warmth of the slab gets into the occupation or into the occupants. Variable fan coils, variable air fan coils is another one that should be considered. Just a fast snippet. The fan coils can have a DC fan. They can be reduced there, not only the water flow that comes into the fan coil, into the coils, but the air coming from the fan coil. So if there's no load, the speed of the fans decrease, and they supply less air because there's no thermal load. So in that sense, reducing the fan of the fan speed, they reduce the fan energy, and they are a means to achieve low energy ratings as well. These definitely systems should be considered, which it is already in offices. Future systems. This system is implemented in our design, but it's worth mentioning to the ones that want to implement to propose very low energy systems. This is a phase change material. It works as a natural ventilation system, but it works night and time, so night and day, in the sense that it can cope with the cooling load of an office. It cools the phase change material at night, and then during the day, when it gets very hot, that material is cold, which is getting cold at night. It throws out again all that cold into the air during the day. So it's night loading of cold, and during the day, that cold that is stored in your phase change material is thrown out through cold air into the space, but there's no compressor. There's a small fan, but there's no chiller needed to cool the air. You could put it if you have high stream loads, put a heat pump. But in essence, you could, I think, in Ireland, is something to be considered if you want to avoid a chilling system. You still need radiators to heat up the space, but anyway, that's another option to be considered. And the last one is, for this particular case, it links to circular economy. That's a concept that you should get into, we should all get in related to it. An aerobic digester. For this particular case, the client said, which is a college, the client said, okay, I have a lot of food waste in my facilities. I have a lot of my grass and as well, so it's the dry waste from my gardens. Can I include design an aerobic digester in my facilities to supply biogas into my building? And it didn't go ahead, this idea, but I don't think it should be disregarded in other campuses or large any place where supermarkets that they have food waste, countryside, hotels, complex that they may have ability to, as I say, manure food waste. Well, there's a chance that this system develop in the future to supply biogas to nearby consumers. Obviously, the small size equipment and aerobic digesters is still you have in the bottom you have an example, but it's not the common thing. The common thing of an aerobic digester is a large facility from a farm, getting the manure from the cows, etc., and then producing locally biogas or even electricity through a CHP. But it is mentioned in the biogas is mentioned in the national mitigation plan again, so yeah, worth considering. And from the electric point of view, previously was all mechanical systems. From the electric point of view, future low energy systems that should be considered are battery storage. If renewables are being produced at night, nobody consumes them because it's the consumption in Ireland decreases, because obviously the activity decreases, but still the wind is there. You still have wind at night in Ireland, obviously, and everywhere else. So what do we do with that wind? Why don't we use it? Well, one way to do it is to store at night, which the electricity is less cheaper. That's one way to night system and use it at night and store it at night and use it in the day. That links with ESB energy storage proposal, which is already in the webpage, which is not really night-day shifting what they are proposing, but it links to it. So will buildings in Ireland in the future will accommodate a space for future battery storage due to the electrification of the network, or the decarbonization of the network, because we are going to use heat pumps. I think we should pay attention to this design item, and we think that it may be possible that we need to allow for battery storage. It's still early days, but maybe if you design a system, a building, and why not expecting a future battery storage to be placed in your building in the near future? So you allow for some space for it in the basement for it. That's an idea. And that's the end of the case 3, and very briefly the end of case 4. I'm moving myself from the education sector. I'm passing myself into showing a very brief example about healthcare sector, and this relates to the design. So this is an operating theater NZEB compliant example that we have tested using the latest NZEB software, which is still a beta test. This has been supplied by SCIA in order to test it, to see how results were obtained. I don't know if you are aware, but the SCIA is developing the new NZEB software, and we have tested in this case study. We are showing you the results and the implications for the use in healthcare application. So basically, what we've decided is this is just an example of the software. And what we have tested is what are the implications to comply with NZEB in an operating theatre, the ones that designed healthcare facilities. Do I need a boiler? Do I need many PV panels? Do I need a CHP in order to comply with NZEB? What are the implications? And this test tries to answer that question to some degree. One of the things to take into account is that the system that it usually being designed in operating theatres is called constant flow and reheat system, which supplies cold air and reheats with coils into the different areas. That's an engineering system to take into account. It also needs to be taken into account that the efficiency of the fans need to increase from the previous regulation. And that means that if before we had allowance to have SFPs up to 2.4, now the software penalizes us if we have fans not efficient enough. And the implication of having fans they are not efficient enough, they need to be very efficient. The implication is that you see it in the slide in the left, in the image in the left, is that the fan needs to be larger and the coil and the air handling unit needs to be larger. And this is an example. So this shows an example for an operating theatre, one SFP, I wouldn't say the old system was inefficient, but let's say the old system minimum requirements against the new air handling unit with the SFPs, the fan efficiency parameter of 1.7, and there's a volume difference of around 30%. So if you multiply for a hospital this by 100 air handling units, so the space could be a bit of difference in terms of the space requirement. Also, we tested the results. We tested, as I say, in order to answer what does it work with the NZEB. Does it work? The boiler does a CHP work? So we obtained two models that comply with NZEB, and those are the ones that I'm going to show to you. One is this one, model 1, we call it. With the test showed that for this operating theatre, CHP plus a boiler plus PV panels, that system comply with the regulation with a new NZEB minimum, with a very low EPC value, which is very, very good, but with 10%, the results on renewables was 10%. So it was just passing. So if just for the ones who are not familiar with it, if the EPC is below 0.9, then your renewable target can be only 10%. If your EPC is above 0.9, then your renewable target can be 20%. So in this particular case, the EPC was below 0.9, then the renewable target only needs to pass to be 10%. And in this particular case, it was 10%, and it ticked the box, it passed. But we had to add PV panels to the CHP solution. So you could assume that for this particular case, that your roof of your building will have to be occupied with solar panels. By PV panels, excuse me. And solution 2 was this one, that comply. It was this one that I want to show to you, and it's quite unusual. Unusual. It's feasible, completely feasible, but it's not the classic one that we see, that we've seen before. And basically, it shows a heat pump working in a cascade mode with a boiler. So and it supplies at low temperature to low temperature coils, which is 50 degrees. So that means that the coils, if you had radiators around the place, they will have to increase in size. But having this, we could have a large boiler serving part of the load, and we have some heat pumps serving part of the load as well. So it's a combined solution to try to cover large buildings, large hospital buildings, a possibility that ticks the box and complies. And as I say, it's not the usual way of that we've dealt with before in hospitals, but just one model and one arrangement that complies. And again, as you see, the renewable target is 10%. So at the EPC as well, it's very good, very low, so easy to comply with the EPC, but not that easy to comply with the renewable target. So again, attention to the compliance with the renewable target. That could be the challenging variable to take into account, and that's why the heat pump becomes an important item, because the heat pump itself gives you that renewable contribution that you need, that you wouldn't have without the boiler. That you would not have with the boiler itself. You need the heat pump to avoid PV panels or CHP, but at the same time contributing to the renewable target. Again, as I say, supply at 50 degrees, 40 return. That means larger coils in the, which you wouldn't care. That wouldn't be a problem with the handling units. That's not really. I don't think that's a really problem at all. Maybe one row in the coil, but if you have radiators, larger units, larger units that you were supplying them at 80 degrees or 60 degrees, as we previously done. So there are all consequences to all systems have consequences and pros and cons. And that's the end of case 4. So in terms of summary, do you want to follow up? That will be the end of all the case studies. That will be the summary for the whole presentation. Just wanted to wrap up as a means of what we've said. In terms of our message, it will focus on the renewable energy, that there are a requirement from the new regulation, the Part L and NZEB, near zero energy buildings. Each project will require a different approach, depending on the size, depending on the use. But the concepts, the concepts that we've explained, they could be considered in all the buildings, in all your designs, if you want to. Attention to the passive loads, attention to the shape of the building, efficient mechanical and electrical systems. When I say electrical, battery storage and lighting, battery storage, well, if it's coming or not, but maybe just to keep in mind, lighting for sure, a main player, light efficiency lighting. Attention to not the carbon emissions, but the high capital cost of renewables, life cycling cost to be presented to the client may be needed to convince them that they need to spend all that money in a heat pump versus a boiler, which is a cheaper classic alternative option. And is electricity to be the fossil fuel? Are we going to stop consuming gas? Is electricity the fuel for the future in Ireland? If it's going to be decarbonized, that's a question mark. And that's all. Ready for questions.
That's great. Thanks a million, Louis, and thanks, Edith. So encourage everyone to type your questions in the text box if you have any questions. I have one here from Stephen I'm going to read out to you now. So he's asking, have you done any studies on the effect of the thermal mass on the renewables required? So for example, the reference building uses a wall thermal mass of 11.7 kilojoules per meter squared Kelvin. If you keep the same U value, but you increase the thermal mass of the wall, e.g. up to 100 kilojoules per meter squared Kelvin, the heating requirement goes up in SBEM. Thus, the amount of renewables required also increases. But in a dynamic model, using the same profiles, the boiler load decreases when the wall changes from 11.7 to 100 kilojoules per meter squared Kelvin, i.e. with the increase of the thermal mass. So do you think that some people will design to meet the renewable energy and introduce low thermal mass in buildings to reduce the renewables required, but then increase the actual energy required to operate the building in reality?
Right. It's a case by case, I think. Sorry, so we're moving the microphone here. Sorry. Thank you for the question anyway.
I think it's certainly true that people will design to meet the regulations, and they'll do what they need to do to get through the regulations. And there are always strange anomalies, I would say, in software trying to get a one-size-fits-all solution. I think it's interesting. Certainly, the studies I've done on thermal mass before have shown that it's the first 50 millimeters of the mass, especially if you're on a 24-hour cycle where you're, flushing out the building at night and have occupancy the following day, that it's really only the first 50 mil or so of the thermal mass that's actually contributing to the kind of environmental moderation and the reduction then in energy for both heating and cooling. So it's actually interesting. I don't think we've done that study yet.
So thermal mass in the college, the building that the case 3 that I presented, is being considered mainly in the overheating studies. That's the main, trying to do night cooling and using that night cooling. So the key variable was we were using IES to estimate and do a CIB-CTM 52 analysis on overheating, and that's where we have detail our studies more than it gives a little bit less on the heating side. It was just comply with the overheating that was really challenging, because the load it could give a bit more heating load, but the main player in our particular case for getting renewables was the heat pump. And in order to comply, how efficient was depending on the efficiency of the heat pump. So that was the main player, and the also in terms of complying with NZEB and getting to BREEAM levels, which I've said that is even better. That you need to be your actual building needs to be even better than complying with NZEB. It was the lighting efficiency. Those were the two main variables that we paid attention to. But yeah.
Okay, so we have another question here. Is it possible to do dynamic compliance simulation for Ireland, just like the level 5 for the UK?
No, as far as we know, so the software that, so as far as I know, the software that is being prepared, obviously this is a question for the SAA, but as far as we know, the SSBEM solution that what they are preparing, I don't think the DSM is being, as far as we know, we don't think the DSM is an option for Ireland yet. But this audience, I think if we all kind of ask for it, but then maybe we could make a point. Absolutely, if the SAA, I think if the SAA, my humble opinion is the SAA realizes there is a requirement for all us engineers for DSM to carry out atrium design and more complex geometries, then let's go for it. Somehow we should present that requirement to the SAA. Yeah, but to my knowledge, no, there's no. The NZEB will be SBEM version, as far as I know.
Okay. So someone's very interested in acquiring the overheating study for the college based on CIB-CTM 52. Very interested.
Yeah, okay. It's an overheating system as well with the Manchester weather data. So yeah, it is. But it's an IES. I mean, in terms of the concept, is that the message is not that particular case. The message is, would you consider doing for your designs? Would you consider first doing naturally hybrid ventilation system where you can allow for temperatures to drift above the normal 24s? Would you be and using CIB-CTM 52 for compliance? One question, one proposal. Second, would you consider future weather data, let's say Manchester 2050, or maybe Belfast if it's available? We are using Manchester, but as any other one, it would be good. Would you consider evaluating that weather data for your designs? That's the query, because that kicks all the design consequences. All the buildings are different. all the applications are different. That's the key. The design is. Would you consider putting that in your design brief? That's the point.
It might be worth mentioning. You touched on it earlier. It was about the three aspects to the overheating criteria. So there's kind of hours above specific temperatures, and there's numbers of hours in any given day above specific temperatures. And what's the third criteria?
Maximum temperature.
Maximum temperature.
Yeah.
And so all three of those are considered in the overheating analysis, and you can fail one of the three, but if you fail two of the three, then you fail overall. So it's actually quite an interesting analysis, really, in terms of how it looks at the different types of overheating.
So for the ones that maybe for the ones who are not familiar with CIP-CT and 52, which is also picked up, I think, in CIP-CB as well, as far as I know, I think it allows room temperature in naturally ventilated buildings. It allows room temperature to drift over the typical comfort levels, but only for a few hours, kind of thing. You drift, but you need to go back. You cannot go, and it's also based on the outside temperature during the previous days. So if it's warm the previous days, then apparently the human being, as per the code, the human being can support higher temperatures. So typically up to 28 in Ireland if the average summer temperature is around 20. So yeah, there are three criteria, and then there are IES is as an example is capable to evaluate in a very easy way that the CIP-CT and 52. And the three criteria: if you fail one, you still comply. If you fail two, you comply with it. But it becomes really challenging if you allow for the future weather data and not the doubling weather. Sorry, we usually design in doubling, but for any Irish weather data, because the present Irish weather data shows that the outside temperatures are not very, very hot, but the Manchester weather data in 2050 shows that temperatures raise up to 32 degrees. So that becomes, in order to design a naturally ventilated building, that's in the future. That means that in the end you will need some sort of cooling to back up, to top up those days that you are very hot. That is very hot, and we cannot see it now because this is future global warming. So difficult to.
Yeah, and it is becoming very important in terms of, if we look at the life cycle of our buildings, they're at least 50 years. So halfway through the design or halfway through the life of the building, they'll be experiencing much higher temperatures, and so that might take down our heating loads, but obviously it will push up the cooling loads. And how you design that flexibility into your buildings now, it's a slightly different topic to what we've been discussing, but at the same time, it is a very important factor in design.
And just on that, is CIP-CT and 52, is it a requirement in Ireland, or is it just a recommendation?
As far as I understand, it's just a recommendation. I can't remember the exact reading, but people could correct me if I'm wrong, but it is mentioned in the text, and I don't think it's a requirement. Okay.
And I've got another question here. Is it necessary to consider mechanical ventilation for NZEB schools? Is it necessary to have mechanical ventilation?
To achieve NZEB?
To achieve NZEB? No, I wouldn't think so. No, you could do natural hybrid ventilation.
Okay, great. Thanks a million, guys. Thanks for all your questions, everybody. That's the final webinar in the NZEB for Commercial series. We have one more on for NZEB for Residential coming up next week. So hopefully we'll see you all then, or for our next set of webinars that are going to be in January of 2019. Okay, thanks everyone for attending. Thanks. Bye now.
Thank you.
Thank you.